Good afternoon, everyone. So this has been a long morning, and my task is in 14 minutes to give you a sense of space and time in fundamental physics. It's interesting that both of the preceding talks dealt with space and time, the way that our brains locate our bodies in space. And we just heard a magnificent description of the history of space and time, of the universe. Space and time are our most fundamental concepts of physical reality. All of our descriptions of physics, of the real world, place particles, objects in space and follow their motion as they move, as time evolves. But if you think about it, you've never actually observed or sensed space or time, for that matter. They are mental constructs that we construct to understand physical reality. And we do that when we are infants, in what I regard as one of the most amazing intellectual achievements that each of us achieved as young infants, as our brains were developing. We developed this incredibly powerful way of describing the nature of physical reality called space and time. We all did this somehow. We have no idea how we did this. We all achieved that. And to my thinking, everything else we ever achieve in our lives is a small achievement compared to our construction of a model of physical reality based on space and time. But given that this is an infantile construction, it's no surprise that the concepts of space and time have greatly evolved over the last 400 years of modern science. And I'll describe a bit of that evolution. So, most of you perhaps have the version of space and time that was best summarized in quantitative terms by Isaac Newton, who constructed the first quantitative theory of motion and of one of the fundamental forces of nature, the theory of gravity, and how it affects motion. And in the Newtonian world, space was a kind of system, a coordinate system, we say, a way of locating objects throughout the universe in a rigid, mathematical system which had no physical dynamics of its own. And time was universal and existed throughout the universe, and you could pick any two events in the universe, and everyone would agree that either A preceded B, came before B, or B became before A. This is perhaps the way many of you still think of space and time. There's space, it's the same everywhere, and time is universal throughout the universe. And this is a very good perception, very good model for constructing a description of physical reality. It works very well in classical physics, and it survived until the 20th century when Albert Einstein, in what I call, version 1 of Einstein's space-time, modified our understanding of what space and time is. Einstein had to reconcile Newton's theory of motion with the extraordinarily successful theory of electricity and magnetism, one of whose consequences was that the speed of light was independent of the motion of the observer. If you measured the speed of light at rest or moving in a train, you got the same answer. And Einstein realized that that required a modification of our understanding of what space and time are if you buy the notion, which Einstein believed in very strongly, that there is no privileged observer. The observer at rest and the observer in a train moving at a constant velocity with respect to the other observer see the same physical phenomena, have the same laws of physics. Einstein truly believed that there is no privileged observer. He also believed that there's no privileged nation or religion or race. And with that combination of the constancy of the speed of light as predicted by the theory of electromagnetism and the notion of no privileged observer, he changed our notions of what space and time are, unifying space and time together. This diagram sort of describes now not space and time, but space-time. So we have space this way, time this way, and you have here an observer at a given point in space and at a given time. If he stands still, he moves, staying at the same point in space, moves forward in time. This is a ray of light. Now, an event C that occurs here at this time cannot be influenced by the observer A because no signal could propagate from A to C. The fastest they can go is at the speed of light. And therefore, Einstein realized that you can't tell whether A happens before C or after C. From the point of view of the observer at rest, C happens later than A. But if you consider another observer who is moving with respect to A, then C will happen before A. There is no notion of absolute simultaneity in Einstein's space-time. This is very difficult to understand, and there are many other strange things that can happen in Einstein's theory of relativity when you move with great velocity. You all have heard of the twin paradox. The twin goes off in a rocket close to the speed of light, makes a journey, comes back after 100 years. We have aged 100 years on Earth, but he has only aged 1 year. And that phenomena has been tested experimentally, not with twins, spaceships, but with radioactive particles moving in accelerators. But that was only version 1. 10 years later, Einstein came out with an even more radical version, version 2 of space and time, because he tried to reconcile his theory of relativity with Newton's theory of gravity. See, in Newton's theory of gravity, the gravitational force acted instantaneously. If somebody moved the sun, we on Earth would immediately feel that. It would change the force that the sun exists on the Earth and change our orbit instantaneously. That was inconsistent with Einstein's theory of relativity, so he had to do something. And he did. He realized that you could extend this principle of relativity, that there was no privileged observer, to accelerated observers, not just to observers moving with a constant velocity with respect to each other. He demonstrated this by the famous elevator Gedanken, thought experiment. He said, consider somebody in an elevator moving in empty space, far away from anything that would pull on them, with a constant acceleration. If that observer dropped an object, it would fall, because the elevator is accelerating upwards. You feel this in an accelerator, right? In an elevator, as you accelerate upwards, you feel a force pulling you down. And all objects would feel the same acceleration downwards, just like they feel an acceleration downwards in a gravitational field, just like we feel a force since the Earth is pulling gravitationally on us. And as Galileo showed, all objects fall with the same speed, with the same acceleration. So Einstein realized that you could make an equivalence between the space and time, the motion in space-time, and the force of gravity. And he realized that space and time is dynamical. If you insert into empty space an object like the sun, it will, in his theory, curve space and time, and then other objects like the Earth will move in that curved space-time. As my colleague in Princeton used to say, Johnny Wheeler, mass energy tells space-time how to curve, and space-time tells mass how to move. So in Einstein's theory of space and time, space-time becomes not just a rigid, fixed coordinate system throughout the universe, but a dynamical object, like other physical objects, that responds to mass and affects the motion of other masses. Now, Einstein's general relativity is well approximated by Newtonian gravity, and that's what we use to calculate, to send rockets to the moon. We hardly need to include the small corrections, in that case, to Newtonian gravity. But it has one remarkable prediction, and that is that if we now shake the sun, the Earth will feel that change in the gravitational force, but after some time. The curvature, the fabric of space-time will shake, adjust, and that change will be transmitted by gravitational waves to the Earth. And it will take 8 minutes, because we are 8 light minutes away from the sun, for us to realize that somebody shook the sun. Einstein predicted that gravity waves in the fabric of space-time should exist. And as you know, recently we have detected them. It took 100 years. And it required not shaking the sun, but colliding black holes, or observing the collision of black holes, objects that Einstein's equations predicted are very strange and have been now understood to be abundant and commonplace throughout the universe. For example, in our galaxy, the center of our galaxy, there's a black hole. And since it's black, light can't escape from it. It's hard to see directly, but you can see the orbits of all of these stars around something in the middle, and using Newton's equations or Einstein's equations, you can calculate that there is an object in the middle there which weighs 100 million times, sorry, 1 million times the mass of the sun. But you can't see it, so most likely it's a black hole. Black holes are thought to populate, to be the center of violent events that we can see across the universe, gamma ray bursts. And indeed, 2 years ago, a little over 2 years ago, the first evidence of gravitational waves was recorded, which appears to be the collision and merger of two black holes. That's an amazingly energetic event in which, when these black holes collide to form another black hole, a significant amount of their mass is converted to energy, creating such an enormous amount of energy that for a fraction of a second, this event emits more energy than all the stars in the universe. And in addition, that event, that shock to the fabric of space-time, propagates outward like a stone thrown into a pond at the velocity of light, and 1 billion years later arrived at Earth and was detected by the LIGO Observatory. Even more remarkably, this year, an event, gravitational waves, were detected from what appears to be colliding neutron stars. Those are collapsed stars with very dense neutron matter. And when they collide, they also emit gravitational waves. But since they're not black holes, there's a lot of stuff around. They also emit light. And this particular collision was reported by the gravitational wave observers to astronomers around the world, who immediately started looking and saw the same event, not just in gravitational waves, but all forms of electromagnetic radiation: X-rays, ultraviolet, optical, infrared, and radio waves. An amazing confirmation of Einstein's predictions of gravity traveling with a dynamical space-time traveling with the speed of light, and a new window onto the universe which will revolutionize astrophysics and astronomy in the next decades. If space and time are dynamical, then cosmology becomes physics. Before Einstein's theory, cosmology was something that religion and philosophy addressed. But after Einstein, the structure and the history of the universe is the subject of physics. We just heard about the amazing discoveries that have been made in understanding this history and the past and the predicted future. But meanwhile, something else happened in physics in the last century, and that was the discovery of quantum mechanics, which has totally changed our understanding of the microscopic world. And this is Planck, Bohr, Heisenberg. That has yielded us an incredibly successful theory of the structure of matter: electrons and quarks, and the three fundamental subatomic forces that act within the atom and the nucleus. What is summarized in what we call the Standard Model, an incredibly powerful and predictive and successful theory, Those equations you can put on one T-shirt. But many mysteries remain. One of them was discussed by Adam, the nature of dark energy, also dark matter. But the most interesting question for fundamental physics is how the forces unify. And when we extrapolate the forces that act within the atom and the nucleus to very high energies or very short distances, gravity becomes important. And so we have been challenged for the last 30 years to unify the forces together with gravity that has taken us in strange directions, like string theory. But the challenge is really the understanding of space and time. Because if we take Einstein's theory and extrapolate it and ask what will happen in quantum mechanics if we look at the dynamics of space and time itself, very short distances, we get a picture which is very confusing, sometimes called space-time foam, and artists picture it as a mess. Space and time are losing, they're not smooth, they're not controllable anymore. So we know that we have to go beyond Einstein's theory. And that's the challenge we face today. One of the handles that we've been led to is string theory, in which particles are replaced by strings. It's a very unifying concept. Its main goal, one of its main goals was to unify all the forces. But it also has challenged in a deep way and given us hints as to how we might once again radically revise our infantile notions of space and time. For example, it asked the question, are there more than 3 dimensions? And in simplest versions of string theory, there are. There are 6 extra dimensions that we can't see since they're so small. But at each point, like this point right here, if we were to look with a very good microscope, we would see an internal, fascinating 6-dimensional space. And many of the questions that we can't answer with the standard model are answered by the geometry of this internal space. We don't know whether this is right. We don't understand this approach well enough yet. But the fact that we can connect fundamental issues like why are the forces what they are, and what is the structure of matter, the value of the quark masses and the electron masses, and all of those things to the shape of hidden dimensions is something that Plato would have loved, reducing everything to geometry. This, however, has challenged us even further. In this approach to fundamental physics, the basic properties that we constructed as infants and have used for hundreds of years of space and time as a smooth geometry with fixed topology and a fixed number of dimensions fade. In this approach, none of these axioms necessarily hold. And we're faced with the idea that we believe more and more is that eventually we will understand that space and time, with our present notions of space and time, will be understood as approximations. Space and time, in a sense, will be an emergent concept from something deeper. Gravity as well. Gravity is dynamical space-time. We have and have been exploring for the last 20 years an exquisitely precise example of such an emergent space-time based on string theory, in which we have both open strings, closed strings, and a dual description of physics, either using a quantum mechanical system with no gravity and sometimes no space, and a system of strings moving in space-time. I don't have time to describe this. I'm totally out of time. But it has started to enable us to understand the strangest objects in the universe, black holes, which appear to lose information. As you drop things into black holes, you lose information. And Stephen Hawking famously claimed that this violated quantum mechanics. And now, with this duality between quantum mechanics and geometry, we can relate black holes to objects we understand very well and show that information is not lost. So, and finally, the other thing that is suggested by this challenge to space-time is that maybe we can begin to understand how to approach the Big Bang. In Adam's picture, you start after the Big Bang and observe until today. But what happened at the beginning and what will happen at the end? How did the universe begin? Again, a question that physics is now challenged to ask and has, in my opinion, the potential perhaps to answer. The universe, according to Einstein, is the physical history of space and time. It has a beginning, has an end. And we don't yet know what the rules are, but we're now faced with that challenge. So, how do the forces unify? What is space-time made out of? And what fixes the beginning of the universe? That is the challenge we face following Einstein's encouragement, and I'll end with that.